So I want to wrap up our conversation about inverses today um, by looking at some word problems that involve inverses. Um, but first, let's ask this question. A few bell work problems would be good here. If f equals, or f of x if you like its more formal name, cube root of x plus 1 minus 2, can you find f inverse for me? Pause the video, give that a try. Hey, welcome back. So did you remember to switch the x's and y's? X equals cube root y plus 1 minus 2. And I would add 2 to both sides. I still need to get rid of this radical. So I'm going to cube both sides of the equation. Notice I'm not cubing the x and the 2. I'm cubing all that stuff. I'm cubing the whole side of the equation. Here, these cancel. We have x plus 2 cubed equals y plus 1. And all we need to do now is subtract 1 from both sides. X plus 2 cubed minus 1 equals y. And then we could say, well, this isn't just y. It's f inverse of x. Okay, nice. Next question for our bell work. Number 2. Which of these is 1, 2, 1? And we've got A that looks like this. And we've got B that looks like this. We've got C, which looks like this. And D, which looks like this. Okay, which of these is 1 to 1? Oh, and provide a reason. Well, we know if a function is 1 to 1, we know that that function, for every input, there's only one output, but also for every one output, there's only one input. And that means that we have a function, and that function has an inverse that is also a function. And those are really the only inverses we're concerned about, are inverses which are themselves a function. Knowing that something has an inverse tells us more than actually trying to make the inverse. We could confuse ourselves and lead ourselves to believe that things that do not have an inverse that is a function are things we can find by making an inverse. This sounds very confusing. So let's just get through that and I'll show you what I mean. So which of these is 1 to 1? Well, here this input only goes to one output, and here this output only goes to one input. So this is pretty clearly the case. But if I also understand 1 to mean this thing has an inverse, then really graphically my preferred method is the horizontal line test. And with the horizontal line test, I see this one and this one pass the horizontal line test, and therefore these functions are 1 to 1. This one, yeah, and this one, they both pass the vertical line test. These are functions over here, but they fail the horizontal line test. And so these are not 1 to 1, which means these do not have an inverse unless we restrict the domain to include that. Okay. I was going on for a moment there about inverses. So for example, if I have x squared plus 2 And I want to make the inverse of this. I switch the x's and y's, and then I solve for y. Don't forget that square root. And here we are. Now, at this point, I've gone through all the algebraic steps. You know, you're more than welcome to say this, but that's not true. This looks like positive square root of x minus 3, but also negative square root of x minus 3. This fails the vertical line test. This is not a function, therefore, we can't have a function inverse. No, this doesn't work, okay? So just because I can switch the x's and y's and solve for y doesn't mean the result is going to be my inverse. It doesn't work that way. I have to actually, I have to know before I start that process that this thing is going to fail the horizontal line test unless we restrict its domain. Without restricting its domain, this has no inverse. So there's no reason to do all that algebra stuff. But it does require me to really think about, hey, is this even possible? Just because I can doesn't mean it is. If I restrict the domain here and say, okay, for x greater than or equal to 0. Well, sure, now I'm only looking at this part of the graph, 0, 2, 1, 3, 2, 6. And so what points must exist on the inverse function, right? This part passes the horizontal line test. Well, let's see. From these points, I can build the inverse by switching the x's and y's. So there's going to be a place out here called 2, 0. And then there's going to be a place here called 3, 1. And there's going to be a place over here called 2, 6. There. And we're reflecting across y equals x. Yeah, so if I restrict the domain on this parabola, then sure, that can have an inverse. I can certainly see that inverse graphically, but I can also make that inverse. Y equals x squared plus 2, x equals y squared plus 2, x minus 2 equals y squared. But now when I take the square root of both sides, because of this, I'm only interested in the positive one here, not the negative one. You want the negative one? Change the direction of that inequality. There we go. All right? Okay. Now, I want to talk about this function, new function, last bell work problem. And this function has as its domain negative infinity to infinity, and has as its range 2 to infinity. Okay? So this is what I know about f of x. So I kind of want to ask the question, providing f of x passes the horizontal line test, or is 1, 2, 1. Providing either of these things is true, could you then please find f inverse? What could you say about f inverse? I mean, it's clear I don't have an algebraic representation here. I don't have a graphical representation here. All I have is this information here about domain and range for f. So what would be true for f inverse? Good. That's right. So if this is domain, these are the inputs, these become the outputs on f inverse. Likewise, these outputs on f become the inputs on f inverse. We're switching the x's and y's here. That's all we're doing. Okay, so let's move on. I'd like to consider the following. yeah, let's consider the following. Um, if we have a function, a equals pi r squared, um, for r values greater than 0. This is the formula for area of a circle, and to be equal to 0, you don't have much of a circle if the radius is 0. So I kind of want to leave that off right now. But my question is, what's this mean? A of 15. Let's say that r is measured in centimeters and a is centimeters squared. So how am I to understand a of 15? What's going on here? Well, we know from our functions unit that this is an input, and the input variables on this function are radii number in centimeters. So we're plugging in 15 centimeters for the radius. And this is asking the question, what's the area going to be when we plug in 15 centimeters? So if I plug in 15 centimeters, I've got 15 times 15, which is 225 pi. So I know that a of 15 is 225 pi. I even know that because this is an area, an output from this function, that the units would be centimeters squared. Okay, area always has square units. So I understand this as I plug in a 15 centimeter radius, I get out a 225 pi centimeters squared area. So I would say, if someone asked me to write a description of what does this mean, when radius is 15 centimeters, area of the circle will be 225 pi centimeters squared. Okay? All right. So now let's ask this question. A inverse of 15. What's that mean? How do I find that? Well, that's a good question. Maybe I should, build that inverse function. So we'll switch the inputs and outputs. R equals pi a squared. And so I've switched inputs and outputs. I'm going to divide by pi. To get from a squared to a, I need to take the square root of both sides. And so I get a equals square root r over pi. And that sounds fabulous. And so this, we know now that we've solved for a, this is supposed to be a inverse, right? Okay, so yeah, I'm supposed to plug a 15 in. I'm supposed to plug a 15 in here. Okay. Yeah, I feel a little uncomfortable with that. And here's why. It's really uncomfortable. My input on the original function, the input was radius. And the output is area. Okay? Now, what happens when we make an inverse? Now, the input is area, and the output is radius. And I have a problem with that. I mean, that's perfect. That's correct. There's nothing wrong with that. My problem is over here, because it sure looks like here we've said input is area. If we're talking about the inverse function, if we're talking about the inverse of this function where input was radius and output was area, when we flip those, we've now got input is area and output is radius. So what's that symbol mean? You know what it doesn't mean? It doesn't mean radius. And that's really, really hard for students. They knew that input R was radius, and they knew that this symbol meant area. And so, what? This isn't radius? No, no, it's not. No, this is the input on the inverse function, and the input on the inverse function is area. That's supposed to be our area number, which means the output is supposed to be radius. This is very, very upsetting. It could well be very, very confusing, but it's very upsetting to me. It's very upsetting because I knew in the original situation that R represented radius and that A represented area. And I followed all the directions from yesterday. I switched the inputs and outputs and solved for the output. I did that. Yeah, we had this, remember? And so now I'm thinking, I plug a radius in here and I get an area. But that's not what this says. This says that you're going to switch the inputs and outputs. And so your input now should be an area. Well, this is my input, and that is not an A. And my output is radius. Well, there's the output, and it certainly doesn't look like radius. So I'm hoping that many of you, if not most of you, understand what I'm talking about. Switching the inputs and outputs, it's not working for me here. Why? It worked yesterday. It even worked during the bell work when I took those points, those ordered pairs on the graph of the function, and then flipped the x's and y's on the ordered pairs, and there I had a graph of the inverse. Why isn't that working here and now? And the answer to that question has to do with what these symbols mean. That's it. They actually have a meaning. It's because we've imbued this symbol with that meaning and this symbol with that meaning that this process doesn't work. The way we did it yesterday, where we always started by saying, let's switch the x's and y's. Well, word problems are different. They're just going to be different. No, they're not going to be harder. They're just going to be different. And by different, here's what I want you to do. For word problems, don't switch the inputs and outputs. Don't switch them. Instead, simply solve for the other variable. And what I mean by is, right now this equation is solved for A. You want to find the inverse? You solve this equation for R. Make it so that this says R equals. All right, well, I'll divide both sides by pi. And now I'll take the square root of both sides. We've already got this restriction in place, so I'm not going to have a plus or minus. I'm just going to have square root of A over pi equals R. Now that's okay. That I like. I like that a whole lot. Remember, with the original function, the input was radius, and the output is area. The inverse, therefore, the inverse function should switch that relationship. We should go from plugging in a radius and getting out an area to plugging in an area and getting out a radius. And look, that's what this says. I plug in an area and I get out a radius. This is how we deal with word problems, okay? Don't switch the inputs and outputs. simply solve for the other variable. That's all we're going to do here. Because if I switch these, I'm now saying that this symbol over here is still radius. No, that's not going to work. We can't do these word problems the same way we handled all those inverse building techniques from yesterday. So simply solve for the other variable. A inverse means R is the output and A is the input. I'm going to plug in an A, I'm going to get out an R. On the original function, we plugged in an R and got out an A. See how they switched jobs? But we didn't switch the variables here and solve for the other one. We simply solved for the other variable. We had been solved for A, we've now solved for R. Okay, so that's kind of big and new and different for inverses. We're not going to be switching those variables. So if we go back to this problem for a moment, okay, and I asked you about A of 15, and we said, okay, what's the area when radius is 15 centimeters? So what about this? What's that mean? The input on the original function is radius, and the output is area. The input is radius, the output is area. So what does that mean this is? That's right. This is not a radius. If on the original function the input was radius and the output is area, when I'm looking at the inverse function, the input is area and the output is radius. This is asking the question, what's the radius when area equals 15 centimeters squared? Okay, and that's kind of important. It's definitely ACT important. Yeah, we need to be thinking about that. Okay, so let's consider the following. My dog is involved in this next function. T of H. T, tail wags. H, hot dog bites. Okay, here's my function. H to the third plus 4. So, 1. Is T of H a one-to-one function? Okay, how come? Right. We know that this function is a cubic just shifted up 4, and so we're looking at something like this and this. I plug in an H, I get out a number of tail wags. Okay, I probably don't have any use for this stuff over here because I can't have a negative number of hot dog bites. But this function, sure, passes the horizontal line test. So of course, even in its original state, still passes the horizontal line test. So I know there's an inverse here. Okay, let's make that inverse. We pause the video and make the inverse. Okay, did you get t minus 4 under a cube root equals h? Me too. Wait, you're saying you had something different? You had this? Well, that doesn't make sense to me at all. Why doesn't that make sense? Well, I think the person who comes up with this did this. we were looking at t equals h to the third plus 4. Then they said h equals t to the third plus 4. They said h minus 4 equals t to the third, and they took the cube root of both sides. And so now I know that t equals cube root of h minus 4. And I would argue that this is not at all right. How come? Well, look at our original function. The input to our original function was hot dog bites, and the output was a number of tail wags. So if instead of talking about the original function, I wanted to consider an inverse, wouldn't I be, come on. If the input here is hot dog bites and the output is tail wags, the inverse should be the input is tail wags and the output is hot dog bites. That letter does not fire in my brain as hot dog bites. That letter definitely does not shoot off neurons in my brain that says tail wags. Not at all. So we did a wrong thing, and that wrong thing was we switched the variables. Whenever we're doing a word problem, don't switch the variables, just solve for the other variable. And so I get h equals cube root of t minus 4. And this makes me much happier. This is t inverse. This is t inverse because originally we plugged in hot dog bites, we get out tail wags. So the inverse function, I should be plugging in tail wags and getting out hot dog bites. And that makes sense in my brain. Because these letters have meaning to them, many students get confused when making an inverse in a word problem situation. So instead of going to the confused place, just solve for the other variable. I solved this one for h. That's my inverse. That's t inverse. So tell me, with all that conversation in mind, what will make sense of this? T of 2. So that's 2 to the third plus 4, which is 8 plus 4, which is 12. What are the units on that? What is the meaning of this algebraically, that t of 2 equals 12? Well, we know when you give the dog 2 hot dog bites, there will be 12 tail wags. Input is hot dog bites, output is tail wags. Okay, so that's understanding that. But what if I change this now to be, hey, t inverse of 31. Are these hot dog bites or are these tail wags? On the original function, I plugged in hot dog bites. I get out tail wags. On the inverse function, that's got to be tail wags. And I'm looking for how many hot dog bites. This says if there are 31 tail wags, how many hot dog bites? Will you need? Okay. The input is tail wags. The output is hot dog bites. We can certainly go about solving that equation. Remember, we had h equals cube root t minus 4. This is the inverse function. This is t inverse. Okay. I'm supposed to plug this in. See? It's tail wags. See, I'm plugging it in. So 31 minus 4 is 27. And the cube root of 27 is 3. So we know that h would be 3. How many hot dog bites will there be? You will need 3 hot dog bites if there are 31 tail wags. All right? All right. So I think we're beginning to get a little more comfortable with that. But I kind of want to push it just a little further. There's an old Albanian saying, yes, and I am, in fact, half Albanian. In fact, my first language wasn't English, it was Albanian, because my great-grandmother was taking care of me while my dad was at work and my mom was in college. So there's an old Albanian saying I learned. Albania, it's a country on the Adriatic. It's kind of north of Greece and south of Serbia. All right, so here's the saying. If you have figs in your haversack, then you will have many friends. Okay? A truer sentiment has never been said. Figs, that's a type of fruit. Haversack, think backpack. Think book bag. Okay? So if you've got tasty fruit in your backpack, then you're going to have lots of friends. And so what I want to suggest is that we consider a situation, a function, if you will, a function of figs and haversacks, or a function of relating figs and friends. Big F for friends as a function of little f figs. Okay, and let's say that is 2f plus 1. So I plug in a number of figs that I have, and my output is how many friends. Great. So with that in mind, will you please tell me what f of 21 is, what its value is, actually compute f of 21, but also tell me its meaning. What does this mean? Yeah. Because I know that I can evaluate this. Oops, sorry. That's what I want. I know I can evaluate this big F function by plugging in 21 here. 21 times 2 is 42. 42 plus 1 is 43. What's that mean? I mean, I can evaluate a function. I've been through the functions unit. I get an output. There was an input. But what does this mean in the context of this situation? Well, we know that the input here is figs. And we know that the output is the number of friends. So, when I have 21 figs, I will have 43 friends. Input figs, output friends. Okay? If I have 21 figs in my haversack, I have 43 friends. So tell me then about this. F inverse of 21. What's that? How do I find that? Okay, so the first thing I want you to do is find what this is equal to, and then I want you to explain what it means. Okay, remember that big F of little f was 2 little f plus 1. Am I going to switch the big and little f? No. I'm just going to solve for little f. Big F minus 1 is 2 little f. And if I divide everywhere by 2, I get that little f equals 1/2 big F minus 1/2. Fabulous. And I can see my input is now a number of friends, and my output is a number of figs. When I see this inverse, this number is a number of friends. Friends go in, and figs come out. So I've got 1/2, 21, minus 1/2 is going to be 20 over 2, or 10. What are the units on that 10? Not friends. No. These are figs. If you have 21 friends, then you have 10 figs in your haversack. Again, the original function, f of little f. Our original function, the input was figs, and the output was friends. This means that on the inverse function, the input is friends, and the output is figs. How many figs do you have in your haversack? Okay? Okay. I like that. Yeah, there's a worksheet for you to do on interpreting the inverse. That's definitely something that's going to show up on this unit test. So I will say, yeah, that's something. If you feel like you have time and energy now before our class over this material, you might want to look at some of those problems, especially while this is fresh in your head. I actually want to address this situation for a moment because many of you are still really tentative about composition. And so I want to go through a nasty composition problem. 2x minus 1 over 3 minus x, and g equals 4x plus 3 over 3x plus 2. Okay? And what I want to do is I want to determine R, F, and G inverses. What did we say we could do to verify if these two were inverses or not? Do you remember? In that last video, we said if you want to verify that two things are inverses, then you need to do f of g, and you need to do g of f, and both of those need to be equal to x. Okay? So will you do one of these and see if you get x? And maybe some of us will do this one, and some of us will do this one, and we'll then be able to determine whether we both get x, if one of them gets x, or if neither of them gets x. Okay? So try one of these. I'm going to start with this one first when you come back. Okay, I'm supposed to plug g of x into all the x's of f of x. Well, this is f of x, and here are the x's of f of x. So I have to take all this and plug it in there, and I have to take all this and plug it in there, because I'm doing f of g of x. I'm going to have 2 times 4x plus 3, 3x plus 2. And don't forget that minus 1 also up there in the numerator. And then in the denominator, I've got 3 minus, and instead of that x, I'm putting in all of g of x. 4x plus 3, 3x plus 2. Okay, so here's where I am now. Now what is it that I'm supposed to do? Well, you know, when we did problems like this in the Algebra Basics unit, we said, hey, let's make a common denominator. And here, in order to combine these, I'm going to make a common denominator. Fabulous. So how does this tidy up? Okay, well, way at the top, I've got this minus this. So distribute that 2 up there. I'm going to have lack of room. 8x plus 6 minus 3x minus 2. This is really important to distribute that not just here, but also here. Okay? Over our common denominator, 3x plus 2. Down here on the bottom, I've now got 12x plus 9 minus, don't forget to distribute that, 4x minus 3. And again, we have over 3x plus 2. Okay, so I've got that complex fraction. I have a better sense of why we were looking at those last month. And so what's up? Well, 12x minus 4x is going to be 8x. And 9 minus 3 is 6. On the bottom, we've got 3x plus 2. But what about up here? Well, 8x minus 3x, that's going to be 5x. And 6 minus 2 is 4. This is also over 3x plus 2. And so now I'm going to flip and multiply. Okay, so I flip and multiply. What does that give me? 5x plus 4 times 3x plus 2 over 8x minus 6. Well, this doesn't look like F and doesn't look like G. So what does that mean? Well, it means that these things aren't inverses of each other. I do believe that these functions are one-to-one, but remember, if these functions are inverses of each other, then when I plug one of them into the other, I should get x, but I don't get x. So let's just confirm. We took this and plugged it in there. Yeah. And then on the bottom, we took this and plugged it in there. Yeah. No copy errors there. We then made a common denominator on the top. We remembered to distribute. And here we made a common denominator on the bottom by multiplying over here by 3x plus 2 over 3x plus 2. Did I really do that step? I think I did that step. I seem to have erased it, so I'm not entirely sure I did that step. So this is 3x plus 2 over 3x plus 2. That's going to be 9x plus 6. Huh. What's missing here? Oh, no, it is. That's my G. 3 minus x. Plug that into all the x's. This is me making a common denominator. I see the 4x minus 3. I see the 12x plus 9. I should have a 9x plus 6. Oh, I like checking work. So how does this combine like terms? Oh, 5x plus 3 over 3x plus 2. Okay. Well, it feels a little better, but it's still not. When I did the composition, I should have gotten x, and this is most definitely not x. Okay. Though, I do think it would be nifty keen if now, before you left, you did g of f of x. What happens when I plug in f into all the x's of g? Don't be scared, go slow, and don't forget to make a common denominator after you substitute. Okay? All right, go try it out. Hi, welcome back. So I'm going to take this and put it into each of those x's. So I'm going to have 4, 2x minus 1 over 3 minus x. Don't forget this plus 3 over 3 times 2x minus 1 over 3 minus x plus 2. Okay, now is the point where I make that common denominator. This needs a 3 minus x over 3 minus x, and this needs a 3 minus x over 3 minus x. So what's going to happen next? Well, I'm going to have 8x plus 4 plus 9 minus 3x over 3 minus x over, and now here I'm going to have 6x minus 3, and that's a positive 2 times 3 is 6, and minus 2x, all over 3 minus x. Okay, so let's combine like terms. I get 5x plus 13 over 4x plus 3. And if I flip and multiply, sorry, that's 3 minus x. I'm going to have 3 minus x over 4x plus 3. These cancel, and I'm left with that. I do see a 4x plus 3, but here I have it in the denominator, and here I have it in the numerator. And this time I have a 5x plus 13, and that is not. So there's composition. There's composition with complex fractions that you should be comfortable with. And there's the knowledge that we already feel comfortable with complex fractions. So just don't freak out when you're asked to do something like that. Go slow, make a common denominator, and you'll get there fine. All right, let me know if you need any help. Take care.